Hello viewers, welcome to LMS Solution. Today we are going to see about Consortium for Electric Reliability Technology Solution, microgrid test bed. Okay, so how we are going to simulate this microgrid test bed by using Matlab. Okay, so today we are going to see about this simulation. Thanks for watching our videos and kindly subscribe our channel and also click bell icon for a notification about upcoming videos. So first I'm going to explain about the paper on CERTS Microgrid Laboratory Test Bed. So here you can see that. So this is the microgrid test site. So created by CERTS. So it consists of different elements. So one is utility grid, and then here they have a load. So it going to be considered as feeder C, and then it have micro source B1 and then corresponding load, and then it have micro source A1 and then corresponding load, and also another micro source A2 and then it have another load. Okay, so here that utility voltage is going to be considered 33 kilovolt, and then this feeder voltage is going to be considered as 11 kilovolt. So here that this feeder voltage going to be considered as 33 kilovolt, and then this micro source going to be considered as grid connected PV. So this micro source going to be considered as grid connected wind turbine or wind generator, and then this micro source going to be considered as grid connected battery storage element. Okay, so here this operating voltage will be around 415 volt. So here also the operating voltage will be 415 volt. So here the operating voltage will be equal to 33 kilovolt. Okay, and then you have to use the different loads here in the feeder, and also the feeder A1 and A2 going to be connected with that means the distance between this feeder, this A1 and A2. Okay, the length which is equal to 100 yards. Okay, so this thing is going to be implemented in the Matlab. Okay, so next we go to see about that Matlab detail about this microgrid test site. So here you can see that. So this is a Matlab simulation or Matlab model of that CERTS micro test bed or site. So here we are consider 33 kilovolt main grid or utility grid, and then it going to be stepped down to 11 kilovolt by using this transformer, and then here we have that local load. So in grid we would have local load. So load here we are using 40 kilowatts, and also we have reactive power around 5 kVA. Okay, so next, so here we are using static switch, and then so here you can see that we have another transformer. 11 kilovolt is step up to 33 kilovolt here, and then you will be connected via grid connected battery system, and also we have that load, some load, The load data is equal to 30 kilowatts. So next we go inside that grid connected battery system. So this is the block inside that grid connected battery system. So we have battery and then DC link capacitor and grid inverter along with the transformer. And also it have battery controller and inverter controller. Okay. So in battery controller we have to provide a PQ reference. Okay. So based upon that PQ reference, so you have to generate IDQ reference. So how much current, how much real and reactive power is going to be taken from the battery to the that utility grid. Okay. So for that we have some. So this is a calculation used for calculating the IDQ reference based upon PQ reference as well as real power from that grid inverter. Okay. So that means so here we are going to measure that grid inverter power here and then reference power, right? That means real and reactive power going to be compare here, right? We have to compare real and reactive power, actual and reference, and then process via real power control and reactive power control. So it will generate IDQ reference. So this IDQ reference will be is given to that inverter control. So and also you need to measure the grid inverter voltage and the current. So inside this, first you need to convert that the grid inverter voltage and current into DQ form, right? ABC to DQ form, and then here we need to compare. That mean we need to compare that actual current with the reference current, and then we need to for that been processed via PA controller. So here we are going to use that feed forward control also. So finally we will get VDVQ control signal. So next we need to convert that VDQ control signal into ABC form. So here we are going to use a DQ to ABC conversion. Okay. So after that, that ABC, actual ABC control voltage or control signal is processed by a PWM generator, and then it will generate the pulse for that inverter. So here we are getting that pulse. So this pulse will be given to grid inverter. So here we are having neutral clamped inverter, and then we have harmonic filter to smoothen that voltage from that inverter, and then here we have step up transformer from 415 volt to 33 kilowatt. Okay. So and then you can connect it with that utility grid, right? So this is the block inside that grid connected battery. Okay. So now the battery grid connected battery is connected with this utility. Okay. Next, the same point we are going to connect this load also 30 e power 3. Next, you can open this model. We can fix the power rating for that battery, grid connected battery. So here I fixed the power rating is around 50 kilowatts, and then battery nominal voltage is 480, and battery capacity is 500 Ah, and then grid side line to line voltage is 33 kilovolt. Here we need to change grid frequency is 50 hertz, and then the simulation time step is 1 e per minus 6 and the controller time step is 1 e per minus 4. So next, here we are using that step down, that mean transformer, that means this side we are having 33 kilovolt and this side we need to convert to 11 kilovolt. Okay, so next you can see here the same utility grid, right? We are connecting that grid connected solar PV array. So the rating of solar PV array is 41 kilowatts, and then grid side line to line voltage is 11 kilovolt, grid frequency is 50 hertz, and then simulation time step is 1 e per minus 6 and controller time step is 1 e per minus 4. We can go inside this solar PV grid solar PV system. So here you can see that it have solar PV panel, DC link capacitor, grid inverter with the harmonic filter and transformer, and also we have inverter control. The inverter control have MPPT as well as inverter current and voltage controller. So we need to measure this grid inverter voltage and current, and then PV voltage and current, and then voltage across this DC link capacitor. And then here we have to process that PV voltage and current via that PN to MPPT algorithm. So it will be provide that reference voltage, and then it when we compare with that DC link capacitor voltage. So next it when we process via PA controller, the PA controller will provide the ID reference current. So next here you can see that the grid inverter voltage and current going to be converted into DQ form by using ABC to DQ, and also you have to use PLL now to generate omega T. So after that we have to compare that reference current with the actual current here. So here you have to compare that reference current with the actual current in the DQ form, and also here also we are going to use feed forward control logic, and finally we will get the controlled voltage or controlled signal in form of DQ. So next, so we need to convert that control voltage or control signal in the DQ form into ABC by using DQ to ABC conversion. So here finally we'll have control signal in the form of ABC. So next you got to process, that means it's processed by a PWM generator. Finally we will get a pulse here, PWM pulse. So that going to be given to that neutral clamped inverter. So here, and then you have to use harmonic filter to filter the harmonic present in the inverter output side, and then you have to use step up transformer to step up from 415 volt to 11 kilovolt, and then finally the output of this solar, that means grid connector solar system connected with this feeder. Okay, and it have the local load also. The local load is going to be taken as 20 kilowatts, 20 kilowatts, and then the micro source, this source and this source have the distance around 100 yard feeder. Okay, So the distance of the feeder is 100 yard, right? You have to mention this line length. And then here we are using DFIG wind turbine, and then we have step down transformer here 33 to 11 kilowatt, and then here we have the local load 20 kilowatts, right? So open this one. So this is the data of generator 45 45 kilowatt divided by 0.9, and then stator voltage around 33 kilowatt and 50 hertz frequency, and turbine data is 45 power 3, that will 45 kilowatt, right? And then wind speed at nominal speed at CB maximum will be equal to 11 meter per second. Here the initial wind speed will be considered as 11 meter per second. So here you can provide that wind speed. So you can vary the wind speed here, and also you can provide the reactive power requirement here. Okay, the output of this wind turbine is around 33 kilowatt. It going to be stepped down to 11 kilowatt by using this transformer, and then it going to be connected to the feeder. Okay, so next you can see that. So here we are going to measure the voltage of this load VCL, ICL, voltage and current. So here we are going to measure the wind turbine voltage and current here. So here we are going to measure the voltage of this load VCL1, XCL1. So here we are measuring that grid connected solar PV system voltage and current here, and also we are measuring that PV panel power. So here we are measuring that voltage of grid connected battery system and current of the grid connected battery system, and here we are measuring that mean corresponding load voltage and current. So here we are measuring the secondary, that mean utility grid transformer secondary voltage and current. So this is the primary of the transformer voltage and current. So here we are measuring this load voltage and current. Okay. So and also here we are using another thing, I think, but statecom. So here statecom used for reactive power compensation. So it consists of multi-modular MMC model with each phase having 22 power model. Okay, this one. So each phase having a separate full bridge MMC. Okay. So here we are going to measure that voltage of that each full bridge MMC, and it's going to be connected to the utility grid. Okay. So to control this three full bridge MMC, so we have two control loop or control two level of control. So one is higher level control and lower level control. So here we need to measure grid voltage and current, and also we have to provide reactive power reference. So based upon this, we need to convert that mean ABC into DQ form by using transformation, ABC to DQ transformation. And then based upon this Q reference, you have to generate IQ reference based upon Q reference in the ABC. Okay. So after that, we need to process that VDQ IQ reference and then voltage of that full bridge MMC. So you have to generate the gate pulse for that each full bridge MMC. So this is nothing but a gating pulse for that each full bridge MMC in the statecom. So finally, this going to be given to that full bridge MMC in order to supply or absorb the reactive power based upon the Q reference command, right? So here you can fix reactive power detail here. So you can fix positive reactive power or negative reactive power. So the statecom detail. So we can see the statecom detail in the scope, right? That means we can see the grid voltage, grid current, and then first converter, full bridge MFCA converter voltage, and then Q reference, actual reactive power. Okay, everything you can see in this scope. So here you can measure the load 4 voltage and current, load 6 voltage and current, and battery bus, that means grid connected battery voltage and current, and the load 3 voltage and current. Here you can see that secondary grid transformer secondary voltage and current. So this is grid transformer primary voltage and current, and then we can see the load 5 voltage and current. Here we can see the grid generator solar PV system voltage and current, and here you can go, here you can measure the different powers. That means you can measure that different load power, right? And then we can measure the power of grid, power of PV, power of wind, power of battery, and then we can see the detail here, right? So here we can see that grid power and then solar. So here, so this is nothing but battery power. So here you can see that grid power, solar PV power, wind turbine power, and battery power. So now I'm going to simulate this model. So finally we can see that result of the model. So here you can see that variation of grid power, solar PV power. So here you can see that solar PV power is maintained around 40, right, nearly to 38 kilowatt, right? Sorry, not 80, so 40.5 kilowatt, right? So here you can see the wind power is maintained around 20 kilowatt, and here you can see that the battery power is maintained around 33 kilowatt. Here you can see that the variation of that grid power, PV power, wind power, and battery power. Okay, so here you can measure that grid power, solar PV power, wind turbine power, battery power. So next we are going to see about the different details. That means here we can see this is the wind bus voltage and current. So here you can see that. So this is battery bus voltage and current. So this is PV power, so PV voltage and current. So this is secondary of the grid transformer voltage and current. So this is secondary of, so primary of the grid voltage and current, and then here you can see the load 4 voltage and current, this one. So this is load 6 voltage and current, and then we have load 3 voltage and current. So here you can see that this is the single, that means single phase full bridge MMC voltage and grid voltage. So the both will be having in phase. Okay, and then this is the current of the grid. So this is the voltage of that each full bridge MMC, and then you can see here. So the blue color will be actual reactive power. So yellow is the reference. So here that statcom will be supplying the reactive power with the tracking the reactive power command, right? So these are the result can be taken from this CERTS microgrid test bed, right? So this is operation of this simulation model. Thank you for watching our videos. So kindly subscribe our channel and also click bell icon for notification about upcoming videos. Thank you so much.